Dynamic programming is a systematic approach to solving complex computational problems by breaking them down into smaller subproblems. These subproblems often overlap, meaning the same calculations are repeated multiple times when using a naive recursive approach. Dynamic programming avoids redundant computations by storing the results of solved subproblems and reusing them whenever needed. This makes it a more efficient alternative compared to recursion or divide and conquer techniques. Unlike divide and conquer, where subproblems are independent, dynamic programming is particularly suited for problems with overlapping subproblems and optimal substructure. It is most commonly used to solve optimization problems, where we need to find the best possible solution, such as maximizing revenue or minimizing costs. Dynamic programming operates in two ways: a top-down approach with memoization or a bottom-up approach using a table. By leveraging these methods, we can transform problems with exponential time complexity into those with polynomial time complexity. Dynamic programming is based on two key principles: optimal substructure and overlapping subproblems. Optimal substructure means that the solution to a problem can be composed of solutions to its subproblems. For example, in the rod cutting problem, the maximum revenue from cutting a rod can be determined by finding the optimal cuts for smaller rods and combining their revenues. Overlapping subproblems occur when a problem is divided into smaller subproblems that are solved multiple times. Dynamic programming addresses this by storing the results of subproblems in a table, allowing future computations to reuse these results without recalculating them. This reduces the computational effort significantly, making dynamic programming much more efficient than a naive recursive approach. Solving a problem with dynamic programming involves four systematic steps. First, characterize the structure of an optimal solution. This step identifies how the problem can be divided into subproblems and establishes the relationships between them. Second, define the solution recursively. Use a mathematical recurrence relation to express the value of the solution in terms of smaller subproblems. Third, compute the values of solutions to the subproblems. This is often done in a bottom-up manner, solving smaller subproblems first and using their results to build up to the solution of the original problem. Finally, construct the solution. After computing the necessary values, use them to reconstruct the optimal solution, such as by determining the sequence of decisions that lead to it. These steps form the core framework for applying dynamic programming effectively. The rod cutting problem demonstrates the practical application of dynamic programming. The problem involves cutting a rod of length n inches into smaller pieces to maximize the total revenue from selling these pieces. Each length has a specific price, and the goal is to determine the cuts that yield the highest revenue. For instance, suppose a rod of length 4 inches is given, and the price table indicates that cutting it into two pieces of 2 inches each provides the maximum revenue. The challenge lies in evaluating all possible ways to cut the rod efficiently. Without optimization, the number of ways to cut the rod grows exponentially. However, dynamic programming solves this by avoiding redundant computations, making it an efficient solution. The naive solution to the rod cutting problem, known as the recursive cut rod algorithm, calculates all possible ways to cut the rod. This approach has exponential time complexity because it repeatedly computes the same subproblems. For example, for a rod of length n, it considers 2 raised to the power of n minus 1 possible cuts. Dynamic programming optimizes this process using two approaches: top-down with memoization and bottom-up. In the top-down method, results of previously solved subproblems are stored and reused, avoiding redundant calculations. The bottom-up method systematically solves all subproblems from the smallest to the largest, storing the results in a table. Both methods reduce the time complexity from exponential to a more manageable order of n squared, making the algorithm much faster and more practical. Dynamic programming can optimize the rod cutting problem through two approaches: top-down with memoization and bottom-up computation. In the top-down with memoization approach, the recursive solution is modified to store the results of subproblems in an array or hash table. When a subproblem is encountered again, the stored result is retrieved, avoiding redundant computations. This ensures each subproblem is solved only once, significantly improving efficiency. The bottom-up method solves subproblems incrementally, starting from the smallest. Each solution is stored and reused to solve larger problems. For the rod cutting problem, the algorithm computes the maximum revenue for a rod of length 1, then length 2, and so on, until the solution for the entire length is reached. Both methods transform an otherwise exponential problem into a polynomial time solution, achieving theta of n squared time complexity. The bottom-up cut rod algorithm demonstrates the bottom-up dynamic programming approach to the rod cutting problem. This algorithm solves subproblems iteratively, storing the results in a table to avoid recomputing them. The algorithm begins with the smallest subproblems, such as determining the revenue for rods of length 1. For each rod length up to n, the algorithm considers all possible cuts, calculates the resulting revenue for each, and selects the maximum. The solution for the rod of length n is stored in the final entry of the table. This approach avoids the exponential growth of recursive calls in the naive method and ensures a time complexity of theta of n squared. An additional advantage of the bottom-up approach is its systematic traversal of all subproblems, ensuring no subproblem is missed. This makes the method robust and reliable, even for larger values of n. The matrix chain multiplication problem is a classic application of dynamic programming. It involves determining the optimal order to multiply a chain of matrices to minimize the total number of scalar multiplications. The order of multiplication dramatically affects computational cost. For example, consider three matrices with dimensions 10 by 100, 100 by 5, and 5 by 50. Multiplying them in one order requires 7,500 scalar multiplications, while another order requires 75,000. The problem does not require actually performing the multiplications. Instead, the goal is to determine the sequence of operations with the lowest computational cost. Dynamic programming provides an efficient way to solve this problem by evaluating all possible parenthesizations and selecting the one with the minimum cost. The process involves breaking the problem into overlapping subproblems, solving each once, and storing their results for reuse. The matrix chain multiplication problem relies on two key properties: optimal substructure and overlapping subproblems. Optimal substructure means that the solution for multiplying a chain of matrices can be constructed from solutions to smaller subchains. For example, if the optimal way to multiply a chain of matrices splits it into two subchains, then the multiplication of each subchain must also be optimal. Overlapping subproblems arise because the cost of multiplying specific subchains is calculated multiple times in different parts of the problem. For instance, when determining where to split the chain, the cost of multiplying a subchain is reused. Dynamic programming addresses this by storing these results in a table, avoiding redundant calculations. This systematic approach ensures that each subproblem is solved only once, resulting in an efficient algorithm with significantly reduced computational complexity compared to a naive recursive method. The matrix chain order algorithm is a dynamic programming solution to the matrix chain multiplication problem. It uses two tables, one to store the minimum number of scalar multiplications required for each subchain, and another to record the optimal split points. The algorithm solves the problem in a bottom-up manner, starting with the smallest subproblems. It first computes the cost of multiplying chains of length 1, then length 2, and so on, until the full chain is optimized. For each chain, all possible split points are evaluated, and the one with the lowest cost is selected. The resulting tables not only provide the minimum cost but also describe the sequence of operations needed to achieve it. This method has a time complexity of theta of n cubed and a space complexity of theta of n squared. Compared to a brute force approach that evaluates all possible parenthesizations, this dynamic programming solution is exponentially faster and practical for real-world applications. The matrix chain order algorithm exemplifies how dynamic programming transforms seemingly intractable problems into efficient, solvable tasks by leveraging overlapping subproblems and optimal substructure. The longest common subsequence, LCS, problem is a classic example of dynamic programming used in string analysis. The problem involves finding the longest subsequence common to two sequences. A subsequence is a sequence derived by deleting some or no elements from the original sequence without changing the order of the remaining elements. LCS is particularly useful in areas like bioinformatics, where it helps compare DNA or protein sequences. For example, given two sequences X and Y, the LCS problem seeks the longest sequence Z that is a subsequence of both X and Y. Unlike the longest substring problem, LCS does not require the subsequence to occupy consecutive positions in the original sequences. To solve the longest common subsequence, LCS, problem using dynamic programming, we first define a recursive relation.
Let Ci, j, represent the length of the LCS between the first I characters of X and the first j characters of Y. If the ith character of X equals the jth character of Y, then Ci, j, equals Ci1, j1, plus 1. Otherwise, Ci, j, equals the maximum of Ci1, j, and Ci, j1.
Using these relations, we fill a table in a bottom-up fashion, starting from the smallest subproblems and working up to the full sequences. Once the table is complete, we can trace back through it to reconstruct the LCS. This approach ensures a time complexity of O of m times n, where m and n are the lengths of the two sequences. The longest common subsequence, LCS, problem uses dynamic programming to find the longest subsequence common to two sequences.
Define Ci, j, as the LCS length of the first I characters of X and the first j characters of Y. The recurrence relation is if I equals 0 or j equals 0, Ci, j, equals 0. If Xi, equals Yj, Ci, j, equals Ci1, j1, plus 1. If xi does not equal yj, ci, j, equals max ci1, j, ci, j1. Fill a table bottom up, where cm, n, gives the LCS length. To reconstruct the LCS, trace back from cm, n. Move diagonally if characters match, or follow the larger value, left or up, if they don't.
This algorithm efficiently computes the LCS with O of m times n time complexity and provides both the length and sequence. Dynamic programming solves the optimal binary search tree, OBST, problem by defining a recursive relation for the expected search cost.
Let ei, j, represent the minimum cost of searching for keys between I and j. To compute ei, j, we consider all possible routes and calculate the cost of each configuration. Using a bottom-up approach, we fill a table with these costs, starting with the smallest subproblems.
For each range of keys, we select the route that minimizes the total cost. This method has a time complexity of O of n cubed, which is feasible for moderate-sized problems. The resulting tree is optimal in terms of average search time and is widely used in database indexing and other applications.
The optimal binary search tree, OBST, problem uses dynamic programming to minimize the expected search cost for a set of n keys with known probabilities. Let ei, j, represent the minimum cost of a subtree containing keys I through j.
To compute this, we evaluate all possible routes k between I and j. The cost is the sum of the subtree costs and the total probability of the range, and we select the route that minimizes this value. Using a bottom-up approach, we first compute costs for small subtrees and then build larger ones iteratively. The algorithm has a time complexity of O of n cubed and a space complexity of O of n squared. OBSTs are widely used in databases and search optimization to ensure efficient access times. The versatility of dynamic programming lies in its ability to adapt to diverse problems by leveraging memoization and tabular methods. Its success depends on identifying the problem structure and ensuring that subproblems are solved efficiently and reused effectively. As a robust technique, dynamic programming continues to be a cornerstone of algorithm design, driving innovation in areas like machine learning, data analysis, and systems optimization. By mastering its methodology, one can unlock solutions to problems previously considered intractable, making it an invaluable tool in the modern computational toolbox.